Uh, can you hear me now? I hope yes. So, hello everyone. Uh, Unfortunately, the topic today was spoiled, so maybe the following problem won't be so surprising when we solve it. But today we are going to focus on Cartesian trees. Uh, and if you don't know anything about them, I hope by the end of this lesson you know what they are and when to use them, more importantly. I started with uh, giving you this task called floppy. Uh, did anyone have a chance to look into it? If so, does anyone want to share some ideas? So I think otherwise we can start discussing this problem now. Did most of you have time to read it and think about it? Uh, I'll assume yes, that it is indeed the case. Everyone read the problem. Okay, then we shall start. The problem asks us to uh, create a bit sequence of minimum length possible. I think this length, they call it M, I think. Yeah, an array of M integers. Oh no, M are the number of queries actually. Wait, do they actually say at any point in time what the maximum length should be? Oh yeah, they compare it by N. Okay, good. Um, so yeah, by the formula that we have over here, we notice that if they tell us we are supposed to return an array of length L of bits to, so okay, sorry. The problem asks, just to be clear, to encode a given sequence of distinct integers into a bit sequence such that given the only the bit sequence that we constructed from this array, we can answer queries of the form, tell us what the maximum on the interval from A to B is, without actually knowing the values, only knowing those bit values. Technically, the bit sequence that we send could be equal to just the bit sequence of each number concatenated. So we convert every single number into base 2, and then we send that sequence. Unfortunately, what we are supposed to do is compose a sequence of length that should be equal to twice the size of the array. So then only if all the values that we get are up to 4, we may not get the full points for the task. Okay, let's see how we could start working on the problem or how we may think to solve it. So, my tablet's okay. It's working now. So the issue is, as I've said, a trivial solution could impose that. This is such a good joke. Okay, so V1, V2, VK. If we were to send the bit string of V1, that's concatenated with every other bit string. Obviously, we will get enough information that because we'll basically get the initial vector that we can answer range maximum queries. The problem is that we are not really interested, uh, as we see in the task, of what the values are. Whereas here, by the encryption method that we use, we do have extra information when we answer any query. And we really shouldn't. It really means that this solution is obviously suboptimal. End of that. To start things off, let's say that we know when we want to encode the array that bm is the maximum and unique because it says that the sequence has distinct integers. Value of the array. This is it. Again, not key. Then a thing that we might instantly notice is that if somehow we could say that any single interval that passes through M uh, respects for any interval that passes through M, the answer will be M. Then we would basically solve almost half of the queries. What I often like to do, but in this case it will be a bit useless, sort of, is to imagine when it comes to describing intervals like this, what plotting them into a 2D matrix would look like. So segment LR would be uh, placed as a cell on corners on the cell of at row L and column R. Uh, Naturally, such a description would sort of look like this. So there is this main diagonal that represents all the degenerate segments that are over here, which are of the form L is greater than R. So you can see that the row associated with this cell is greater than the column it should represent. And over here are the valid segments that do exist. So here are all of these are valid segments. What I mean now by we could tell every interval that contains them that m is the maximum is that if m would be at this position, basically, uh, all such intervals, and usually this is useful in other tasks sometimes, uh, are of the following form. They form a uh, rectangular region in this 2D description. So we should technically fill all of these cells somehow, or the answer for every single one of these cells should be M. But then obviously the question remains is that if we want to fill up this matrix, and so far we're doing a pretty bad job at that because we can send an actual matrix full of numbers. That's even worse than what we had before. But let's say we want to fill out this matrix. We need to fill out these other uh, regions as well with values. But then we notice that basically what we have over here is uh, these values that were not filled. They form the array from v1 to vm minus 1. And also, same goes for the second triangular region that we have left and unsolved so far. Is it understandable, sort of, where I'm kind of going with this? Although right now it leads technically to nowhere, but does everyone follow me? Okay. The question then remains, how could we tell every interval that contains m that m is the maximum? Well, let's assume that we have a structure that does answer these queries for the left half and the right half. Okay. Then maybe uh, I wouldn't know how to introduce this even more gradually, but let's obviously put m between uh, whatever between should mean these two structures. Uh, in the case that we do so, M should have a higher priority than whatever other things might influence any query from either L or R. So let's assume there is a query uh, LR. If it contains M, it should have a higher priority than anything in either L, which is the data structure or whatever construction we do that solves the entire left half, and R is a structure that it's a black box that somehow tells us an answer for the right half. So anything in either L or R that normally is responsible to queries being answered should have a lesser priority than whatever we give to M, sort of intuitively. This this isn't informatics. This isn't this isn't informatics. This is just sort of vibing so far. So don't worry if you don't understand how to implement this because I'm not actually describing any implementation. Neither L or R. Um, yeah, matrix is, I mean that we, and this is very useful sometimes, especially in sweep lines where you have queries for like point L and R, and I hope we'll cover that sometime later. One would plot uh, every segment LR into a matrix at the point on the row L and column R, and it generally looks like this. Uh, Maybe this idea that we have that we should construct something and insert new elements in the middle with higher priority uh, leads us to think about ancestry or like yeah uh, direct edges or something like that. So we should sort of maybe draw an edge maybe from M to every other thing in L or R that might answer queries such that we would tell them, hey, M is much more important than you. So if you want to answer a query, please check with M first or something like that. And then because we think to include such a unidirectionality, why not just say we will draw an edge from M to L and R, whatever M, L, and R are. But then assume that we would actually do this, and that we will draw an edge from M to L to R. Then what will we have by the end? Well, we'll have a construction that is basically the structure that we sought to describe by blackboxing L and R that sort of does answer, that might be able to answer queries. How? So then assume there is a query LR. And let's check where L appears in the array, uh, because this is obviously a segment from like 1 to n, and where R appears. If we look at what I've drawn here, basically, we see that L and R do not contain M. So then sort of they should remain with L, obviously. Similarly, if L is all the way to the right side and R is also in the right side, then because it doesn't contain M, M shouldn't be the answer to the query. But look at such a case when L is in the left side and R is on the right side. Why did it help us to uh, draw an edge between M and R and M and L? Well, in such a case, if L is what we deduce by induction, some node in L, because if we say that this is the final construction, obviously at every single point we'll just add the new node. And L should also be a construction that is formed of nodes and edges. If L starts in the left half and starts in the right half, then we see that any path that we'd expect that might arise should pass through M as well. So then we can just say that maybe by the end, whatever we should have by the answer of a query from L to R should be the maximum or something like that on the path from L to R. because we're obviously going to construct something that looks like a graph. So then we have our intuition right now, and that's everything that we need to see that this path that we've chosen, this construction that we've come up with, might give us a good solution. Okay. So to formalize all of this, and maybe this is a bit too late, uh, we will say the following. Let V be an array and M the index of the maximum element. So far, also, I want to know that I said that maybe now we have an intuition of where we are supposed to go with the solution, but obviously, in no way, shape, or form can we actually estimate right now that the solution will actually get 100. So please have some faith, both in your solutions and mine, when you come up with uh, crazy ideas. Because obviously, right now, all we did was like, think about some stuff. Until we formalize it, until we describe it mathematically and so on, we cannot know anything. And it is very important that anytime you'd have any solution for any problem, you'd first try to go through all the details on a piece of paper rather than going all out implementing. It's just word of advice. The maximum element from in the array. Then construct a tree uh, with the elements from 1 to n minus 1 and n plus 1 to n. Then let the roots of these left and right trees be L and R. Draw an edge from M to the root of L and from M to the root of R. Then return this new tree whose new root is M. Now that we actually have something concrete to work with, rather than, oh, I'll draw some edges, I'll put M and L and so on, let's look at how we would actually answer a query like this. So similarly, as I've said before, let's look at the entire tree, but I hope now I can draw because it will actually help. So let's say we have a permutation, maybe 3, 1, 6, 4, 5, 7, 1, 4, 3, 2, or something. How would we construct the tree by these rules on this permutation? We will start with node 7 and because this is the maximum value, and then split the array into two halves with the left side and the right side. And then we take the maximum from the left side, which will be the root of the left side. Also, we take the maximum on the right side, which will be the root on the right side. Then we construct the trees similarly on the left and then on the right. On the left, then it further splits into solving these two halves. And then we draw the edge from 7 to the roots of the left side and the right side, respectively. So we have indexes. Now we will label the nodes with the indexes of the positions that they correspond to in the actual array. And what do we see? If we want to have a query that starts somewhere in the left, aforementioned left side and ends in the right side, then it should take an index from one of these. But we notice that basically the entire left side is by definition a subtree. So let's say we want to solve the query from 4 to maybe 9, and we want to get a maximum. Well, what now naturally we might think, because we have chosen two nodes in a tree, what is the path between those two nodes? Well, it starts with 4, goes into 5, then 3, then 6, 8, and 9. We notice, as I said before, that we essentially done what we really wanted to do at the very beginning. If you could tell every interval that contains m that m is the maximum, then we've done our job. And because we've put m between the whatever left side was that we're going to construct and the right side, and we've united them like that, we now notice that we do include 6 on the path, which is important. But more importantly, 6 is the LCA of 4 and 9. Is that clear why this happens? The edges between the nodes. Wait, what edges between what nodes? Never mind. Okay. Uh, does everyone understand why this would happen, or should I explain more? Why the LCA of uh, any two indexes like this will actually give the index of the maximum element. Is it clear for everyone? If not, I may repeat. So this happens because when we split the array by the maximum position, the position of the maximum, right, and then we construct a tree or whatever on the left, on the right side, and also a tree on the left side. I'll wait for some minutes. Yeah, and I'll just finish this and then I'll give a brief pause. Any index on the left side will start somewhere in the tree of the left side, but then to get a path from L to R, you notice that these two halves are disjoint. They are completely separated, and they are united only by the maximum, because that's what we've constructed. We just said that. Uh, and so, what would the path would look like? Well, something on the left side. Then we have to go on the maximum. Then we have to go in the right side. But because we said this is has a higher priority and basically is the root, then by definition it will be the LCA of L and R. Okay, I will wait for 5 to 10. Yeah, sorry. Now it works, I hope. Okay. So we noticed that LCA in from L to R in construct tree, in the tree that we constructed with these rules that I mentioned before, um, is the maximum on the segment. And we do not know the value or anything because it isn't encoded. Uh, which is uh, great, really. Uh, and yeah, that's it. Uh, I guess that's it. Uh, this is useful because it technically tells us that maybe the structure that we have over here squeezes out more information and may only answer to exactly which we need, to the things that we actually need. We only need the index. So then maybe if there is a way to describe this tree from this array V in a way such that it only takes n 2 times n bits, then we might be very good off. We might solve the problem. A first attempt, and I won't get into it because it's pretty useless, in fact. First of all, we notice that this is a binary tree. And because it is a binary tree, it means it has an in order. It is in order of 3 is in order of the left plus the root plus the in order of the right thing. And obviously, this in order is 1 to n. It's just identity permutation. And I think there is like a introductory exercise on trees that if you are given a binary tree and you are given both its in order and its pre-order, then you uh, you can describe the entire tree. And because a pre-order is just a permutation, maybe it's a bit better than sending out each bit string because it's log of n factorial at best case, which still is n log n, but it's log n instead of log max value. But we might have also sent like the just a permutation, uh, just the initial permutation of the elements, and it was the same thing. So this is really a bad thing. We don't need this much information. Um, how do we construct the tree? Okay. Uh, I'll just jump into it because I don't know how to introduce it any further, unfortunately. Let's look at this tree over here. Wait, now it's to okay. Let's look at node one. Let's say that we want to construct the tree just for whatever reason by iterating through elements one by one from left to right. So we start with node one. Although I've said the tree is normally constructed by taking the maximum and then dividing on the left side and the right side, let's see if we can construct it some other way, one by one. Why? I don't know, but let's say so. Um, okay, or another thing that might help anyone. Okay, let's actually discover some more properties of the tree before we get into that. So let's look at some node, let's say 6, and check who is its parent. Naturally, if X would have a parent of P, it means that P used to like solve some sequence LR from the recursion. P was the maximum from L to R, and then X was the maximum from this L to P minus 1. So because X is the maximum, uh, then there are no greater elements from X up to P. In this case. So for 6, there are no greater elements between 6 and 8. And we can notice that, yeah, there's only 5, and 5 is less than both 6 and 8. And so this means that because X is greater than all the elements from in this segment, and P is also greater than all of these elements in the segment, and X is lesser than P by definition, that that P is the next greater of X. Uh, I hope that is clear. No? You understand why that happens? Okay. Uh, good. We can continue. But the issue is the following. Let's look at some other node. For example, I don't know, 10, index number 10. Then obviously because it's like the rightmost value, it doesn't have a next greater. And we see that the that its parent is actually index number 4, which is not the next, but the previous greater. So then how would we know to differentiate between these two cases? Because by the end, actually what we've done is pretty important. We know that the parent of I is either next greater or the previous greater. Uh, okay. Okay. Uh, let's take 6, for example. How would we know that actually 8 is its parent and not 4? There is a little postulate technically that um, if you look at the value at index 8 and the value at index 4, we see that 4 has value 10, while 8 has value 8. So then, if 10 would be the parent of 6, it means that uh, it should be like the second greatest value from uh, the position that uh, this index 4 is the maximum of up to whatever right index it was solving. But then we know that 8 also exists. So at some point there had to be some parent between these two. And that can't really be the case. So it's not really at random. The selection between the next greater or the previous greater is not really at random. Uh, it is actually the one with the lesser value. Because I've kept saying, oh, next greater, previous greater, next greater, previous greater, and so on, we might think, let's actually calculate these values. Let's construct an algorithm that would calculate them. And I think by now we all know that next greater is solved with a stack. Correct? So I'll draw the tree over here again. So this is the tree that we were solving for. Uh, and since we kind of have to calculate, because the next greater is intrinsically tied to the structure of the tree, because we've shown that every single parent is either the next greater or the previous greater. Let's see what happens as we would iterate I think, maximum stack in this case. Yeah, it's the maximum. Maximum stack over the elements from 1 to 10. So initially we start with 2, then we get 1, then we get 7, and 7 is greater than both of them. Initially, let's say that 1 sees that it's next to 2, so 2 should be its parent, and 2 is the root because there are no greater elements than 2. Then when 7 comes, we see that we are greater than both of them, but really not greater than the end of the array because the end of the array is special or whatever. So 7 will pop both of them on the stack. But when we do so, let's see what happens with 2. So initially we assume that it's okay, not next greater, it's previous. I'll do previous greater, not whatever. Initially 2 assume that its previous greater element was like infinity that lies at position 0, which is like a corner case sort of thing. But then we saw that actually 7 7 is also like 7 also has this infinity as its previous greater. So then they can't both have the same parent, because if they both have the same parent and they are both on the same side, then it's not a binary tree anymore. And also we notice that technically if this were to happen, then the LCA of these two elements would be this element that's not in their range. And we said that this is one of the fundamental properties of the tree that we built, that the maximum, that the LCA between two elements is the maximum on the segment, but this is not on the segment. So whatever happened there. Okay. So then what would happen? We know that in this case, because 7 popped 2 off the stack, that 7 is the next greater of 2. And we have to choose between infinity and 7. So clearly 7 is the lesser value. So what we will do is actually draw an edge from 7 to 2 instead and cut the initial edge. And now 7 will be the root. Then number 10 comes and also pops 7 of the root. In the same way, we draw an edge instead from 10 to 7, and then from like infinity to a. Then we get 4 on the stack. We assume naturally now that this 10 is the next greater, it's the previous greater of 4. This is clear. But we will assume that it is also the parent of 4. Then 6 comes, and 6 pops 4 off the stack. Because 6 doesn't also pop 10 off the stack, now we know for 4, both its previous greater and its next greater. So then we have to choose. But we said that we always choose the minimum value between the previous and the next greater. So then what we will do is erase the edge from 10 to 4. We'll draw an edge from 6 to 4 instead. And now we will draw an edge from 10 to 6. And it continues like this. Then we get 5. We assume that 6 is the parent of 5. Then we get 8. It pops both of these off the stack. We know for 6 now that, we know for 5 that its previous greater is 6, but its next greater is 8. And because 8 also pops 6, it means that 8 is greater than its previous greater, so we don't need to change this edge. But because we popped 6 and not 10, we know that 8 is the lesser value between the next greater and the previous greater. So then 8 has to be the parent of 6. And now we actually have an edge from 10 to 8. Then we get 3. We draw an edge from 8 to 3. And then we get 9. We pop both of these off the stack. And again, we erase the edge from 10 to 8 and draw an edge from 10 to 9. So by the end, we will have the following edges. 2, 1, 7, 10, 4, 6, 5, 8, 3, 9. So 2 goes to 1, 7 goes to 2, 4 goes to 7, infinity goes to 4, whatever. Then 6 goes to 4, then 6 goes to 5, 8 goes to 6, 8 goes to 3, then 9 goes to 8, and 10 goes to 9. And this is actually the structure that we always wanted in reality. Is the construction process clear for everyone? So what happened was that we noticed that by iterating the previous greater stack, that we get that at any point, actually for each element, we get both its we can deduce both its next greater and its previous greater. And that the next value Vj of 4 of that. So we have like this. We are supposed to insert Vj instead. We know that for A7 now, that Vj is its next greater and A6 is its previous greater. But since Vj, as I've said, also popped A6, it means that A6 is the lesser value, has a lesser value. So A6 should still be the parent of A7. A5 similarly should still be the parent of A6. A4 should still be the parent of A5. But then A3 should not be the parent of A4 because we know that Vj is the next greater. We know that A3 is its previous greater. But since Vj didn't pop A3 as well, it means that naturally A3 is less than Vj. So then Vj should be the parent of A4 instead. And with this process, we will determine the parents of every node, which actually means we determined the array. Sorry, not the array, the tree. So all we need to send, or a thing we can send to get the answer, is the operations that we do on the stack. What are the operations that we do on the stack? Well, at any point, we may we pop elements and insert elements. But we know that we insert elements on the stack every time that we iterate to a new index. That is, for every index, the set of operations will look like this: pop, 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 and then push. No, not insert, sorry, push. So then we actually have enough information, because every time we see that we push a new element, we know that we iterated through a new index. So we just send this list of operations. Every time we pop an element, we send a 0. Every time we push an element, we send a 1. And since we know that the stack may make up to n operations, QED, I guess. Uh, is that clear? Uh, yeah. I mean, I think if someone figured out this problem during the contest without knowing any of these, which, well, not well known, but they are not like this is a trick that applies to so many problems that one would encounter it at some point, maybe. If someone actually never knew any of these and solved this problem, I'd be like super impressed. But I don't think it's the case. And that makes it, I think this is a bad problem because either you know the trick or you don't. And yeah, how to construct the Cartesian tree using the stack again. Okay, so I said that looking at the tree, we notice that for every element, its parent has to be its next greater or its previous greater or the next greater. Because by the way that we constructed, the parent was the maximum of like some range at some point. Then it was the maximum, and then we solved a sub range on the left or the right. And okay, let's say that we solved it on the left. Then the node, the root of that left side, which draws its parentage towards this maximum, uh, was the greater thing in that entire subtree. So yeah, so this is the maximum, and then this is another maximum, but on this side. So then what follows is that all the elements between this element and its parent are lesser than both m and lesser than both it and its parent. And since its parent is greater, that means that its parent was its next or previous greater. And we also notice that this selection is not arbitrary. I mean, it's not like for this node, I randomly choose if I'll draw my parentage to the next greater or the previous greater, the prev or the next. It's actually drawn to the smaller value of these two. So then we notice also that if you are to calculate the maximum stack from left to right, naturally what most people know is that this will give you the previous greater because you pop all the smaller elements, and then what remains is the previous greater. But in fact, you actually calculate not only the previous greater, you actually calculate also the next greater. Because for example, for this A7, because VJ popped it, it means that VJ should be its next greater. Because up to this point, since we inserted A7 and up to now, it was never the case that we saw a greater element to pop it. And this is the first time that someone pops it. And it pops it only if it's greater than it. So for all the elements that we popped, we know that its next greater is Vj. And for every element, we want the minimum of the lesser, the minimum of the previous greater and the next greater. And so for A7, we actually know, like right in the second that we pop it, who is its left greater and who is its next greater. Its left greater is the element on the stack before it, and its next greater is the element that pops it. And we check if this element also pops its parent, then clearly this is greater than its prev greater. So its parent should be the prev greater. Same goes for A5. Since Vj pops both A6 and A5, then we know that A6 should draw its edge to the minimum of the prev greater and the uh, next greater. But the next greater is greater than the prev greater because it pops it off the stack. So then the parent of A6 will be A5. Similarly, for A5, the parent will be A4 because BJ also pops A4. So then it means the prev greater is smaller than the next greater. But for A4, the next greater does not pop its previous greater. So it means that it's smaller. So then the parent of A4 should instead be VJ, the next greater. And after that, we just insert VJ on the stack and maybe assume that VJ, uh, uh, that the parent of VJ will be A3 until proven otherwise. Is it a bit more clear? So I'll yeah, I'm not working. Can you write the actual code how we link and erase the edges? Okay. Uh, Let me finish this. Uh, so code would look like this. Stack is empty initially. For every element from 1 to n, uh, while uh, while top of the stack is less, less. Top of the stack is less than the current element. So okay, like this. Um, um, Last equals top of the stack, and pop stack. If last is not -1, parent of last is equal to I. Then parent of I is assumed initially to be top of the stack. Then we push I, and that's it. That's the code. So we know that technically we can assume for every element that initially its prev greater is the parent, but the only time that changes is for the last element that we pop. Because for the last element that we pop, as I've shown, uh, the next greater is actually less than its previous greater. So its next greater should be its parent. So we keep track of what the last element that we pop is. And if we actually pop some element, then we should be the parent of that element. Better now? If last No, uh, it shouldn't be inside the loop. So what we do here is we just pop elements. So like in this case, VJ comes and it pops A7, A6, A5, A4. But we know that, so we've shown that A6 should be the parent of A7. A5 should still be the parent of of A6. A4 should still be the parent of A5. So the only time when the prev greater is no longer the parent of an element is for A4 and only for A4. So we don't need to include this in the while loop because it will change the parent of every single node that we pop to VJ, which is wrong because VJ should only have one son on the left and one son on the right. But if both A6 and A7 have its parent VJ, which is like normally I've drawn it over here, but it's like the array is like over here. And if both of these have its parent to be equal to VJ, then it's wrong. Then the LCA of these two elements might be VJ. And as I've said, that's wrong. That shouldn't happen. As we said, the LCA is the maximum on the segment, and it has to be in the segment. We can actually notice, like for VJ, if we were to construct it as I've originally said, with these properties, uh, VJ is the maximum, and we notice that by definition, when this will be the root of some subtree, it will be because Vj is the maximum on a on some segment. And we know that Vj is the maximum on the segment from its prev greater to its next greater. So this is the segment where Vj is the maximum segment on which Vj is the maximum. So then what happens with Vj as we pop all of these elements? Well, we take the list of suffix maxima. So every single element is the maximum on the suffix starting at J and ending somewhere. And we pop until we get to A3. And we notice that A3 is greater than us. So then the maximum of all of these elements is actually the maximum from Vj to its previous greater. So by definition, by the original definition, uh, we should draw an edge from Vj to A4, which is the maximum, because it will be the maximum of the subproblem when we split by Vj. In fact, we can show that the subtree of any element can show that the subtree of any index I will be the maximal uh, segment where I is the maximum value on the range. Okay, so we solved this problem. Hooray. Uh, the next problem, unfortunately, it's on a judge, but it's in Romanian and I can't put it on VJudge because it's not supported. I will share it regardless with you. What's it called? Uh, uh, I will put on Discord as soon as I can log into Discord machine translation for it. But basically, what the problem says is that we are given two arrays. Uh, Yeah, I'm not talking. I'm just writing some stuff. Uh, I leave you to think about this problem. Uh, yeah, I think these are some properties that hold. Uh, there might be some others, but I can't really recall them now. This is the most important of all, in any case. This is a fundamental property, technically. So I guess we should come back at 1620 and hint the solution involves Cartesian trees. Little hint. Okay, so I think we can start. Uh, does anyone have any ideas they'd like to share? The count of committee doesn't matter. It does matter. It should be greater than. I'm not sure what you mean by the count of committee members because they do matter. The count of committee members should be at least as uh, whatever every single person in the committee asks that this value is at least equal to. So then the maximum. No, it says sub array because I think it says in the original statement something like um, since people were found standing in a queue and we didn't bother ordering them in any way, the entire queue will form a continuous subsequence. So otherwise, yeah, technically, if we could have taken a subsequence, then it would have been valid to sort the elements by A and try every prefix if it's valid and if so, what it entails. Because we noticed that the actual issue is like not this, because since B has non-negative elements, maybe I forgot to mention that, but yeah, B has non-negative elements. Um, this is like trivial because we just want the shortest length possible among other things. So you can just say that this is actually equal. Uh, and this is like very easy to like maybe handle. So long as we can actually find some segments that do respect this property because it's kind of hard because you take a random segment and you see that the maximum is some value. And then you think, oh, should I expand R to include more people so that I make this person happy or L? And then maybe after you increase or decrease one of them, then after that, you get another maximum value, and the maximum value changes, and you need to expand the segment more and more and more and more, and it never ends. And it's horrible. Uh, I'll just jump right to it. The problem, like maybe one person can just solve it without knowing Cartesian trees. But the usefulness of Cartesian trees is that they often give you a thing to leverage against and to organize your thoughts on. Whenever you are asked to find segments and something about the maximum on those segments is imposed on you. You have a condition and it says that, oh, you have to do something with the maximum or so on. For this reason, uh, let's consider the maximum Cartesian tree on A, because it doesn't really matter for B. B is just a thing, and we take the sum of it. Really, because we need to leverage the maximum in some way, let's consider the maximum Cartesian tree. Now let's consider a node in it. So, what do we know about this node actually? We know that its subtree, as I've said, contains uh, all the elements from the previous greater to the next greater. That is like previous greater might be over here, that might be an edge, or it might be from the next greater. But we don't really care. We know that the entire subtree of node contains all the values from prev greater to next greater. So for any solution L, and I mean by that respects this basically because we have to iterate over L and R that respect this property and minimize this. So for any solution in LR, any solution LR uh, uh, that starts with L less than node and R greater than node, also max LR equals node, then L starts somewhere in the left sub tree and R starts in the right sub tree. What I mean by this is that naturally R should be like somewhere over here and left should be somewhere over here. And uh, it should be obviously before prev, but if it's in the subtree, then it will forcefully before the prev greater and before greater. So really, we need to just find two indices L and R, one starting in the left side, one ending in the right subtree, such that their length, the length of this segment is equal to the maximum, and the sum on the subarray on its subarray on B is minimum. But we know which what is the maximum because L starts in the left subtree, starts in the right subtree. Their LCA will be node. So the maximum from L to R will be node. So we've basically what we've done is to fix this value because it's the value of node. Now what do we do? How many segments are there that start in the left side and have a fixed length? Essentially, we need to choose path u to be such that I init for I in Cartesian we need to choose path u such that I init. Yeah. But not really. It's not really just on the path, but it's their LCA because if it's their LCA, then we can technically leverage, and we like now know we have like a much better structure on which we can look at, and that's really all there is to it. Have a better structure to look at, for which we know and we characterize better the count of segments um, whose maximum is actually this value because it's all the nodes on anything that starts in the left side and anything not only on the path but their LCA, very important because technically L is on its path, and as I've shown here, like from the path from 4 to 9, this value is also on the path, but it doesn't make any sense. It's irrelevant. It's out of the segment and like not even the maximum. Only the LCA matters. So I ask you this, and everyone can join on the document and write your answers. Um, how many segments? So now what we have is like this. L node R. How many segments start from the left side and have a fixed length, which we know this length is equal to A of node. We have until 16. 32 to answer. 31. You have 40 seconds to answer this. Uh, yeah, I think this is correct. We should see all of the windows using sliding windows. Technically, that is what I'm going to get at. So I'm not. I don't want to really think about what it says here. Wait. So it's the segment. I'm not sure why there is L plus. Because technically this should be enough. This is the count of all the segments technically. Uh, but yeah, we should see all the windows using sliding windows, basically. So a more naive way to think about it is to say that it's uh, the count of nodes in the subtree. Because we can choose like any endpoint over here and we know the length. So we start anywhere over here and then we just take the length and check, okay, maybe it contains node, maybe not, but only those that contain node actually valid windows. So we basically slide this window of length a node. Uh, from like the leftmost element of L to the rightmost element of L. But this is equal to area of the left subtree. Similarly, we can like fix the any valid sliding window by choosing the right endpoint instead of the left point. Because yeah, we can reduce the segment, so it's just equal to the maximum. We don't need to have it like greater. So yeah, it is indeed a sliding window. But I'm not sure if technically we can take every single sliding window. I mean, by the end, actually, it will prove that we can, but analyzing the complexity of this is kind of weird because you'd have to sum up these values. And I'm not sure how one would prove that these values are, that the sum of all of these values is small. But there is a little trick, sort of, that I have in mind to show you. So when we want to do this sliding window, we can actually just either like start sliding the window from over here, and like this, we keep moving towards the left side more and more, or we start from the right side like this, and then we slide the window more and more to the right. And if we do in the first version, by the end we will actually fix every single sub-segment of length, uh, every single possible window that starts somewhere in the left side. We might just assume that. So it will take the area of the left side time. But equally valid is to fix the right endpoint and then slide through all the possible right endpoints, which would take of area R. And both of these approaches are equivalent. They will both give us all the possible candidates. So we can solve, we can calculate all the optimum candidates with max LR to A of node in min of area L, no, O of min, I think, area R. Okay. Uh, do you recognize what this actually leads to? So, and each, wait, not all the AI are equal. Still, we can construct a Cartesian tree. Yeah. So maybe I should have noticed this. Uh, mentioned this somewhere. Let's say over here. Uh, if this is the case, then we can just attribute AI the value of, like, we can give it a pair like AI and I. Then we compare two pairs of numbers A, B, and C, D as follows. Because really all we need to do the stack is like uh, perfect order. I said that we can do stack on a partial order, but that's irrelevant here. That doesn't really matter. Uh, okay, to do stack, we need perfect ordering of the elements on which we apply the algorithm. And because I said we will change the values to have like to be a pair, where one value is the actual value and the other is the index. It might not be immediately obvious how we compare such pairs, but we'll say that AB is less than CD if A is less than C, or A is equal to C and B is less than D. So if this is the case, then obviously there will be no two equal elements, and we will be able to have a Cartesian tree. What essentially this means is that, like, and it gets awkward in some problems. Maybe you'd have to consider the case separately or not, but I guess you learn with experience. Is that like if sort of this thing happens when we have like, depending on how we do the additional comparator here, we might have like either something like this, like the subtrees would be like 3 would have everything from 5 and then everything else. Then 3 would have between the two trees and then everything else, and so on. We notice that still, although this postulate doesn't hold anymore, which I said is the most important one, that like consider an array for which the maximum is equal to 3. Then it will still have one of the trees, one of the multiple trees as its LCA, and then it doesn't actually matter that much because then this segment will be considered uh, at one point by fixing both the left endpoint and the right endpoint, let's say, as to have the maximum equal to 3. So it still holds because look, if we change instead of constructing on AI which are equal and don't really work for the stack algorithm with this, where there are no two elements and there is a perfect order. I'm not sure how that got there. Okay, then what would be the LCA of two elements, A and B and C and D? Well, it will still be the greatest element, but under this perfect order, uh, between the two elements and their positions in the array. It will still give the maximum, but it will be the maximum as defined by this operation. And what will be the maximum? It will be like the element which has the greatest AI, and in case that there will be equalities, the one that appears the earliest. So that still means that it will still be technically the maximum AI. So yeah, and each time looking for each sliding windows takes a lot of time. Normally, uh, yeah, it might take a lot of time. But we notice that uh, we technically have two approaches: start a sliding window in L and fix it one by one and check every time if it's valid, or start the sliding window from the right side and check for each index one by one. Technically, this is like very naive, but whatever. Let's say that we do this. Then, because the two methods essentially they all uh, they will all get all the valid windows at one point. We can uh, do this in the minimum time that it would take either approach. So in O of mean area of L or area of R. That is, either iterate over all the left endpoints or over all the right endpoints. Yes, and now this is actually small to large because if we sum up uh, mean area of the left side or area of the right side for every node, we know from small to large that this is actually of n log n. And so what do we need by the end? We need the Cartesian tree to give us the structure that we need here. Uh, then we need to identify the smaller subtree and then fix every index from it one by one until we find all the valid windows. For every window, then we take uh, the sum on it and compare it to the global minimum. And that concludes this task. Are there any questions? Uh, yeah, I'm glad you like it, but it gets old fast, uh, is what I can say. So these tasks are normally included in the stack homework. I mean, I think there are three problems that talk about something about stacks. This is one of them. This is one of the problems that I've given as homework like 1 week ago. How to come up with this kind of solution. So this is the magic of Cartesian trees. Whenever you have a task, and essentially the task asks you to fix some segment and fix that segment such that something happens with the maximum. In this case, they gave us that we need to find the best candidate where a candidate has to respect these conditions. But as I've given you this new problem as well, for example, in this problem, they tell you to find a subarray such that you also XOR the maximum. We would really love in general to be able to fix this maximum because maximum on a segment and essentially like what is XOR on a segment? That doesn't make any sense. These are two completely different operations. But we can fix this maximum by looking at the Cartesian tree. The Cartesian tree essentially just gives us a better way to handle and actually characterize all the segments that have a maximum equal to some value. And like maybe I'm exaggerating, but 80% of the times it will involve also like something like small to large. Because if you want to fix most of the segments such that they have this maximum that you fix, you might have to fix one of the endpoints in some way. But whenever you see like maximum, you should think, hey, maybe can I do something about Cartesian trees? Some cases it's bad to think about Cartesian trees because they're overly complicated. But sometimes they give you a way to grasp and better understand and model operations that have to do with something with maximum on ranges or minimum on ranges. Clearly, maximum is equivalent to minimum. Uh, is that sort of helpful? Maybe I am mistaken. I actually kind of forgot. But I think Cartesian trees, like sometimes sometimes you will actually use them in the final solution as well. But some other times, like for more advanced problems, I can't really say that I recommend using it because it's sometimes like very hard. Like not very hard, but like unnecessarily hard to use it. I think maybe during the last IOI there was a task uh, in which like I thought about Cartesian trees and it helped a bit because Cartesian trees like give you everything related to maximum. They sort of give you the previous greater, they give you the next greater, they give you the segment where the node is maximum. They also give you like this thing, which is sometimes useful. They give you like all the greater elements to the left and all the greater elements to the right, like all the prefix maxima and the suffix maxima that start from that position. It gives you a lot of things when it comes to comparing things in a stack like that. So yeah, that's it. I'm not sure if we have 30 more minutes. Let's give some hints and take. Yeah. So over here, it's essentially the same thing, but you will find that you somehow have to describe this operation, describe this XORing operation. Again, what I suggest is that you fix one of the endpoints and then check to see. So obviously, if you fix the maximum and the like, subtree, then you know to XOR this value. So then, how do you merge two nodes? That is a completely different problem. That is technically unrelated to Cartesian trees, but Cartesian trees enable you to answer this. Like I give you two segments, find now the maximum XOR that starts in one of them and ends in one of them. But you can fix both of the endpoints at the same time. This was okay. This is like a hard task. This is a counting task, which, as I said, uh, relates to this property that all the ancestors on in the Cartesian tree are all the elements on the max stack, or either from the left to right or from right to left. And here they ask you to do something about the depth of each node. So then, because so normally I've said so far that Cartesian trees help you when you have to deal with like stack things, but in this problem it's the opposite. They give you a Cartesian tree, and it's easier to think about a stack related thing to construct the DP. Although this problem is quite hard, even after you figure this out. Uh, but this helps you to like solve the problem without having to deal with a random tree that you can generate. And this problem I completely forgot, but I remember it's. Wait, why doesn't it work? Okay, too bad. But oh, so Okay, please search the problem on Kyoj.ac instead of here because it doesn't work. This is also something to do with like Cartesian trees, but like I forgot. I can't give you. But here they give you like some buildings and some heights, and they tell you that a segment is good if it doesn't contain any building and it only contains like the sky, and that means that any segment should get for them. So yeah, this is a good resource with more problems on the matter, and I think they have good explanations for the solution of each problem. And two of them I've given you in the homework. But yeah, that's it. The conclusion is whenever you see maximums, think Cartesian trees. Maybe not use Cartesian trees, but think Cartesian trees at first and see if anything comes out of that. I think there was also like a IOI problem at some point. That was the lesson for today. I hope you enjoyed it. And yeah, see you next. Actually, no. I think tomorrow I'm not going to come. I'm sorry. So we might see each other again on Tuesday. So I'm sorry for no Thursday. What did it say Tuesday when I clicked? Oh, because today is Tuesday. Okay, so we might see each other back on Thursday. Uh, Goodbye.